everyone! Welcome to part 2 of chapter 12. Today's lecture is all on titrations and the calculations that go with them. So let's go ahead and get going. So just as a review, we've already learned about acid-base neutralization reactions. So a typical kind of general reaction would be that an acid and a base will react to give a salt and water. So here's an example here. So we have hydrochloric acid reacting with sodium hydroxide. We'll recognize this as an acid because it has an H in the front, and this is a base because it has an OH in the back. So when we have this acid-base reaction, our H from our acid will combine with the OH from our base to make water. Okay, so everything else that's left, like our sodium and our chlorine, that will be forming our salt. Remember, when we make this salt, this is an ionic compound. Okay, so we need to take our ions and circle and switch to make our ionic compound. Here, sodium is Na+ and chlorine is Cl-. So since those are equal and opposite, they just cancel out and we're getting sodium chloride. But if they weren't equal and opposite, you would need to circle and switch to get the formula of that salt. So anytime we're saying salt, these are just ionic compounds. They're always going to contain the cation from our base, so here it's sodium, and the anion from the acid, which here is chlorine, to make our ionic compound. Okay, so we're using these acid-base neutralization reactions to talk about a special type of reaction called a titration. This is a cool process that's used in lab to figure out the molarity of kind of a mystery compound. Let's say you were a really bad chemist and you had a bunch of bottles in lab that were labeled with what they were, like it had sodium chloride and sodium hydroxide, right? They were labeled with what they were, but it didn't tell you a molarity. The molarity is very, very important in chemistry because it allows us to do calculations like we've learned so far. But we could actually use titrations to figure out the concentration of these mystery species, which is pretty cool. So our acid-base neutralization reactions are used in titrations, a really common type of chemical analysis. So in our titrations, we need to know the concentration of one thing, okay? Usually we know the concentration of our base, okay? And the one that we know the concentration of, that is called our titrant, okay? The one that we don't know the concentration of, that is called the analyte. So we have two things. We know the concentration of the titrant, we don't know the concentration of the analyte. And over time, we will add our titrant to the analyte until it is completely neutralized. And once it is completely neutralized, then we can precisely know the volume of base that we added and its concentration, and we knew how much acid we had to start with. We can use all of these numbers to figure out the concentration of our mystery acid. That's pretty cool. So here's how it plays out. We use a special type of glassware in this titration, which is called a burette. Burettes are really precise measuring tools, and so that's why we use them. So here's our burette. It doesn't show all of it. It's kind of this long piece of glassware, long skinny piece of glassware that has markings on it to show how much of our base or our titrant that we've added over time. So here we have a base. That's why you're seeing these little hydroxide molecules, okay? This part of this here is called a stopcock, and you turn it to very, very slowly let out some of this liquid into our flask. Okay, so this down here, this is our analyte. Okay, this is the one we don't know the concentration of. Up here is always our titrant. That's the one we know the concentration of. So over time, we're going to slowly add our titrant to our analyte until it is completely neutralized. So remember, we know the concentration of our titrant up at the top. We're trying to figure out the concentration of our analyte over time. So our burette, right, that piece of glassware, will deliver a very precise amount of our titrant into our unknown analyte. So we will continue adding our titrant, right? We'll continue adding our base or whatever we know the concentration of until we get an exactly neutral solution. Okay, that would mean our pH is equal to 7. It's completely neutralized. That point is called the equivalence point. That means that our acid and our base are completely equal, therefore it's neutralized. The way that we recognize when this is happening is we use an indicator, okay? And our indicator will turn colors when our titration is complete. So before our titration is done, so if it's still acidic, it will be clear like this. But when our titration is complete, it will be a very, very, very faint pink color. You want the very faintest pink. You want it to be so faintly pink that you're questioning yourself as whether it's even pink. Maybe it's still kind of clear, right? But when that very, very faint pink color shows up, that's going to tell you that your pH is equal to 7 and your solution is completely neutralized, which means your titration is done and you can now go about doing your calculations to figure out the concentration of your unknown analyte. Okay, so at our equivalence point, this means there are stoichiometrically equivalent amounts of acid and base. And what that means is that our concentration of H plus is exactly equal to our concentration of OH minus. So we have exactly equal amounts of the moles of those two things. So remember when I was just telling you, you want it faint pink, you want it like super faint pink, to the point where it's almost clear. It's so faintly pink that it's almost clear. That's where the pH equals 7. If it looks like this, even though it's really pretty, if it looks like that, you've gone too far and you added too much base. So this is from a practical standpoint. So in order to get this equivalence point, you want it the very faintest pink possible so that your concentration of your hydrogen ion is going to equal your concentration of your hydroxide ion. And we know the titration is done because that means our pH will now equal 7. Okay, so let's go ahead and do an example of this calculation. So this says if 22.59 milliliters of a 0.1096 molar hydrochloric acid solution is used to titrate 25 milliliters of sodium hydroxide, what is the molarity of the base? So here we're trying to figure out the molarity of our base as opposed to our examples when we were talking about finding the molarity of our acid. But you'll notice you'll always have information about one thing, right? We have a volume and a concentration of one species, and we're trying to find out information about the other. So when we're looking at this, our very first step is to always write a reaction, okay? This is an acid-base neutralization reaction, just like reactions we've done before. So anytime we come across a reaction, we need to write our equation. So here we have hydrochloric acid reacting with sodium hydroxide. So our acid plus a base is always going to make a salt and water. So we would just need to figure out the formula of the salt. Okay, so remember the H and the OH, those will combine to make water. So everything else that's left over will go into making our salt. So we have Na plus and Cl minus, those are exactly equal and opposite. They make NaCl. So again, the first step in doing any type of problem like this is to write out the chemical equation. Then we can go about solving the problem. So remember, we talked previously that molarity is a conversion factor. We will never, ever, 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 ever start a train track with molarity. So then you're left with two different volumes, right? You have a volume here and a volume here. So it's like, okay, well, which one do we start with? Got to start with one of them, but which one? Okay. You are always going to start with the volume that you know the molarity of that species. Okay, so here we're going to start our train track with this volume because then we can use our molarity as a train track to turn that volume into moles. Okay, we'll use this volume at the end when we calculate the molarity of our base. Also, you'll notice the other reason we don't start with this one is because this is the volume of sodium hydroxide, and that's the one we're trying to find out stuff about. Okay, so we'll start with our volume of hydrochloric acid and then use that molarity to turn our volume into moles. Okay, so it looks like this. So we'll start with our volume of hydrochloric acid. You'll notice I have already turned these milliliters into liters. This is to save space on my paper because I know to turn milliliters into liters, I just divide by 1,000. If you would like to include that step in your train track, you totally can. Just remember 1,000 milliliters equals 1 liter. And so you can start with milliliters and use that conversion to turn it into liters, and you'd essentially be starting here. All right, so now that we have our liters of hydrochloric acid, we can use our molarity to turn liters into moles. Remember that molarity is a conversion factor. So when we say 0.1096 molar, that's saying, okay, 0.1096 moles is equal to 1 liter. Okay, so we can use that bit as a conversion factor. So now liters has to cancel liters, so 1 liter will go on the bottom and the number of moles will go on the top. Okay, so again, this step here is just using our molarity as a conversion factor. Once we convert liters into moles, now we can use our mole ratio to turn moles of hydrochloric acid into moles of sodium hydroxide. So looking at the coefficients in our balanced chemical equation, we see that for every 1 mole of hydrochloric acid, because there's nothing here, we get 1 mole of sodium hydroxide because there's nothing there. So we've used our mole ratio to turn moles of hydrochloric acid into moles of sodium hydroxide. So this step was our mole ratio. Okay, you'll notice I wrapped up my train track here. Okay, we're trying to find the molarity of our base. And so a lot of people will ask, okay, well, we didn't find molarity, right? Why aren't you still going? Okay, remember, molarity is equal to moles over liters. So I'm going to use my train track to find moles because I already have my volume. Okay, so now I can use this volume, turn that into liters, and use this number of moles to calculate my molarity. So molarity is going to equal our moles, so I'm just taking that from here. There's our moles. And then we're going to take our volume up here, that 25 milliliters, and you're going to turn it into liters. I didn't show that calculation, but again, you're just dividing by 1,000, or you can use this conversion factor to show a little train track. Okay, so our molarity now is going to be moles divided by liters, and that will get us the molarity of our base. Okay, so to recap, first thing we needed to do is write out the chemical equation. This is a reaction, right? An acid-base neutralization reaction. So anytime we have a reaction, we need to write it out. So we had our hydrochloric acid reacting with sodium hydroxide to give us salt and water. Once we have that written out, then we can do the train track. So we're always going to start with a volume because we cannot start with a molarity. Molarities are conversion factors. You cannot start train tracks with them. So we started with our volume of hydrochloric acid and used our molarity to turn it into moles. We then used our mole ratio to turn moles of hydrochloric acid into moles of sodium hydroxide, which we have here. Once we add our moles of sodium hydroxide, we can use our moles and the volume from the problem to calculate our molarity. And remember, molarity is moles over liters. So I like these problems because they kind of take a bunch of pieces that we've done throughout the semester and put them all together. Now we're writing equations, we are doing train tracks, we're calculating molarity, we're doing, milliliters to liters conversions, right? This is a good kind of review of everything we've done throughout the course. Alrighty, it's your turn to give one a go. This says, what is the molarity of a sodium hydroxide solution if 21.93 milliliters of base is required to titrate 0.243 grams of sulfuric acid? All right, the first step here is to write the chemical equation. Okay, this is just like we've done before. This is an acid-base neutralization reaction. The only thing different really about this problem and the one we did previously is that instead of giving you a volume and a molarity of sulfuric acid, I gave you a mass. Okay, so you'll need to use that mass and the molar mass to turn grams into moles, and then you can use your mole ratio to turn moles of sulfuric acid into moles of sodium hydroxide, and then use the molarity equation to determine the molarity of sodium hydroxide. All right, so go ahead, give this a go, and then come back when you're ready to see the answer. Alrighty, so like I said, our very first step is to write the chemical equation. So we have sodium hydroxide reacting with sulfuric acid. So you need to remember how to, write the formula for sulfuric acid. That's an ic acid, which means it came from an 8 polyatomic ion. So this came from sulfate, which is SO4 2 minus. So if we have H plus and SO4 2 minus, that means sulfuric acid is H2SO4. So sodium hydroxide plus sulfuric acid will give us that. So remember, the H and the OH went to make water. So that means that our salt is made up of sodium and sulfate. So we need to write out those ions and circle and switch. So we have Na plus and SO4 2 minus. So that means that 2 is going to go to the sodium, which gives us Na2SO4. And then you can balance the reaction and you're done with that part. Now we need to go ahead and make our train track. So we're going to start with our 0.243 grams of sulfuric acid. The reason we don't start with the volume of sodium hydroxide is because we're trying to figure out the molarity of sodium hydroxide. That volume is going to go later in the molarity equation. Okay, so we'll start with our 0.243 grams of sulfuric acid. Anytime we have grams, we are going to use the molar mass to turn grams of sulfuric acid into moles of sulfuric acid. So grams will go on the bottom, so grams cancels grams, and then 1 mole will go on the top. Okay. Once we've done that, now we can use our mole ratio from the balanced chemical equation to turn moles of sulfuric acid into moles of sodium hydroxide. We can see that for every 1 mole of sulfuric acid, we are going to react with 2 moles of sodium hydroxide. So we'll end our train track there because that will give us the moles of sodium hydroxide that we need in order to calculate molarity. Remember, molarity is moles over liters. So if we're calculating our molarity of sodium hydroxide, we'll take our moles of sodium hydroxide and then our liters, right? Remember, we can turn these milliliters into liters using 1,000 milliliters equals 1 liter, or just divide by 1,000. So once we've got our moles and our liters, we can calculate our molarity of sodium hydroxide. Alrighty, so today we learned all about titrations, which is a special type of neutralization reaction that allows us to calculate the molarity of an unknown species. It's pretty cool. It's one of my favorite reactions to do in lab. So go ahead and get some practice doing these problems on the Chapter 12 lecture worksheet. You'll need to do problems number 22 to 29. You'll get a lot of practice writing chemical equations, balancing them, and using our train tracks and our molarity equation. So again, I like these types of problems because I really think they bring together a lot of the concepts that we've covered in this class. So go ahead, keep working on this, and if you have any questions at all, please send them my way. I am more than happy to help you out in any way that I can. Otherwise, keep working hard, and I'll talk to you guys next time.